In general relativity context.
So it's really like a follow-up of the talk from Felisa. Thanks for your great introduction on simulation. I think that was really a nice way to speak about that. Because indeed, myself, I never trust my results in simulation completely. At a certain level, yes. Completely not. This talk is based on basically two work. The first one is has been done with Julian Adam and Martin Kumsan. This is about the Gevolution code. This is basically my PhD. And the second part is really much more about numerical relativity, and it has been done with Daverio and Ramses. And this is like my last 1.5 year of work. So this is based on this 4 paper. The paper that explains really Gevolution here is really this paper. It's a long paper that explains how the code works and how you can use it. And this is just a really short letter that explains the scheme that we are using, which I will explain to you now. So during this talk, I will do a really brief introduction, which I've cut because of yours. Then I will speak extremely briefly on that Field2, the framework that we are using for both code, like the Gevolution code and our numerical relativity code. Then I will speak a bit about Gevolution, and then I will spend more time on numerical relativity to finally conclude. So I think this is kind of the pictures that I always start to talk with. All of us know it perfectly well, and I think the interesting thing to say is our goal in simulation is to start somewhere here and to finish somewhere here. This is clearly impossible only with one framework, so you have to use plenty of different codes, plenty of different methodology to go to that point. And in our case, we are interested only on the late universe, so on the large-scale structure formation. Let's say there is no redshift, around from here to here. Basically, you can think about from around redshift 100 to redshift 0. Why we choose usually redshift 100? It's just because at that moment, gravity sector is still linear, and the matter sector is still linear. So you can trust Boltzmann codes to give you power spectrum of your matter content, and then you can build up initial condition for your large-scale structure code. Then, why we want to go while we had this really nice talk about numerical relativity using cosmology, why we have developed this Gevolution code. And I think this is mainly those 3 reasons. Is because basically having dynamical dark energy is quite unnatural in a Newtonian framework where you just have a background which is set by hand. I think it's quite difficult. It's doable, but it's not very. You will have to use plenty of tricks, plenty of assumptions. So if you have a relativistic framework, you can really just put your dynamical dark energy inside your model, and then you will have direct effect on your background. Then relativistic spaces like neutrinos, wormhole, dark matter are really unnatural in a Newtonian framework. I think you can, for example, you have to, if you use Newtonian simulation and you just want to simulate your neutrinos with particles that trace the phase space, you will have to start with particles that have around 5 times the speed of light of speed, which is the only way that you can have to reach something which is relevant at redshift 10 or redshift 5. So basically, in a relativistic model, this is you can put neutrinos or warm hot dark matter. Okay, I have written warm and hot dark matter. I would say that hot dark matter is still a huge problem, but neutrino and warm it's quite doable. The problem of hot dark matter is that you will have too much shock noise in your simulation, so it will be very complicated to get rid of the shock noise. And then there is all the problem of back reaction. It's impossible. There is attempt to test back reaction in the Newtonian framework, but myself I started my PhD working on that for 6 months, and after 6 months I just said, okay, no, let's stop it there, we will go nowhere, because basically you have so many problems involved, from just pure numerics to theoretical facts, like you have very important terms in the virtual formalism are total derivative, so basically they vanish on a periodic box in Newtonian simulation. So going to a relativistic simulation will allow us to study carefully back reaction. And I would say also another thing, that if we are able to tackle back reaction, how to add them in the simulation. So how do we can put back reaction in a Newtonian simulation where the background is completely set by hand and homogeneous. I expect that back reaction will change the scale factor not at the same level at every point in the simulation, because back reaction should depend on your structure. And then you go back up to the top. This is more restriction that are, I think, important to think about, is that if you want to simulate late universe, you have, as Elisa said, a huge spread of scale, or order maybe 10 to the 6, 10 to the 7 order of magnitude to have in your simulation. But you have a really kind of a threshold. It's not very well set. I would say the threshold is between 1 megaparsec and 100 megaparsec. If you look at the literature, they very often use the 80 megaparsec or the 10 megaparsec. So basically, if you go beyond 10 megaparsec, baryonic effect will be extremely important. So then you have to take them into account. And this is clear, because those baryonic effects will be order 5%. So if you want to have a simulation that claims to be precise at the percent level, you have to take care of that. So for small scale, you have to take about baryonic effect, and you have to take into account that the dark matter shell cross. And this is also something that is important, because the visualization is very different if you have matter that shell cross or not. So I would say that basically, if you want to go below 10 megaparsec, you have to use particle, and you have to have fluid description that take care about the baryonic effects. So it means that below these scales, it's like kind of a nightmare for numerical relativity. That this is something that we will not see before 5 to 10 years. I don't expect that. But then for very large scale, you have no shell crossing, because basically your dark matter is quasi-static. It moves very slowly. We all know that. So basically, at those scales, you don't have enough time to let a structure that really shell cross. So there is no shell crossing. So basically, a description of a perfect fluid is quite okay. Then baryonic effects are also neglectable at that scale. So basically, you can describe your system with perfect fluid quite accurately. That's it. So if you just think about the current status of simulation, you have Newtonian simulation with post-Newtonian correction, like gadget, Ramses, ACK. I just speak, okay, now let's say that these are the 3 major codes. These are the 2 European ones, and this is the US one. And you have, in all of those codes, you have a fluid solver and particle solver. In all of those codes, you have a background which is set by hand, and there is no link between the dynamic of your system and your background. Then you have one single code that is relativistic. It's the code Gevolution. I will explain you, it's not at full order, I will explain you what is exactly the approximation scheme which are used. Then in numerical relativity, you have cosmograph, which have been developed by Martin Gibbon and Starkman. That have, yeah, I think it's like 6 months ago or 1 year ago that have put this thing. There is the Einstein toolkit, which has been used by Martin really to do kind of this kind of stimulation. Then there is I mean, not finish this line. So there is Dian and Mitsu, and we have developed our own scheme which is not based on BSSM to do numerical relativity. It's only done with perfect read. We are far away from using particle, and I think that particles are at extremely early stage. You can look at this paper, which is the last paper in a list of 5 or 6 papers that have tried to put particles in numerical relativity. It's the first attempt in the 90s, but if you look at this paper, you can see that basically there is a quite large constraint relation. So basically this paper really states that to have particle, we have to think much more about numerical relativity on particle. So all this work is based on Latitude2. I will just say very shortly what it is. Latitude2, it's a numerical, it's a C++ framework. It's made to work with fields. It works with structured periodic meshes. It's an hybrid OpenMP MPI. It uses a hybrid OpenMP MPI orientation scheme. It has FFT. It uses HDF5 for I/O. So it can handle arbitrary particles, and there is also particle-to-mesh projection, which are embedded in the framework. So let's move to Gevolution. So Gevolution, it's basically a relativistic code, and I would say it's not really a post-Newtonian code because the gravity is really described by a metric. You don't have a direct force particle to particle. You really have the particle which solves the metric, the deformation of the metric, and then the particle evolves on that metric following a geodesic equation. It's an embodied code because particles are sampled by particles. The dark matter is sampled by particles. So if you look at the approximation schemes that we are using in that code, so we start with a very standard metric, and what we do is kind of a very hybrid approximation. First, we use a metric perturbative. We think that metric perturbation remains small at all scales, so we can keep them at linear order. Density perturbation will not remain small, we know that, so we keep them at all order. Then velocity and gradient, it's kind of something which is intermediate between the two, so we decide to keep them at second order. Evidently, this prescription is completely arbitrary. You can probably find your favorite prescription, but why we have done it like that is because we were trying to figure out which term in the Einstein equation are really relevant for cosmology and which one will be completely neglectable. So if you summarize the scheme, we keep all terms in order epsilon square. Basically, in the Einstein equation, you will have all those variables that happen, and you can see that basically the double derivative, we think that is order of the scalars is order 1, and I'm not entering all the details. But with this level, it's in the paper, in the long paper, you can really just do that pure, just write out your Einstein equation, you perturb it, and you keep those terms, and then you're happy. You get exactly what you have. One comment is it's exactly the same procedure that Million-Volt have done for their dictionary between Newtonian simulation and relativistic simulation.
So epsilon is ppn order?
What?
Epsilon?
Yeah, we kept everything up to epsilon squared.
That's basically. Epsilon is v squared over c squared? Is the ppn parameter? What's epsilon?
Epsilon is just like the scale that we consider. It's just to say, to tell you, this we consider those terms like a phi dot phi times psi will be epsilon squared, so we keep it. That's the idea. Or a term like this times this will be also kept, etc. It's just like a simple map to understand what term you will keep in the Einstein equation and which term you will just cross.
David, you said epsilon squared or epsilon? You keep epsilon because you said it was linear, that you kept terms that are linear in the metric perturbations and second order in velocity.
Oh yeah, it's
so it's
epsilon.
epsilon,
In that
right?
table it's epsilon.
Epsilon.
Yeah. Sorry, it's epsilon. Yeah. I had a version with that table. With epsilon square here, epsilon. Honestly, that one is completely. Thank you, Pierre, for this comment. So basically, how do we evolve these things? It's very simple, but there is something which I think it's important to think about. So basically, the main loop. Let's speak about the main loop first. So the main loop, what we do, we evolve first the background, then we evolve we compute the metric perturbation, then we evolve the background, so once again a half time step, and then we evolve we displace the particle, we evolve the particle. And this should sound a bit weird for you, because I've said we have a metric description, but here I'm speaking about the background. And yes, we do a split between the background and not background, but it doesn't mean that the background the background can also be sourced by additional things. This is just a mathematical trick to keep the potential close to zero. Basically, we remove the biggest component, and then it means also that you will have in the metric, in the gravity part, you will have a zero mode. So basically, your background will be the background that we have through a Friedmann-Anderson-Walker equation, and we have in addition to that zero mode of our metric that should be added to this background to get the complete background. That's it. So a few results. About Gevolution, this is quite old, but it's like now 1.5 years ago. So here you have the power spectrums of the component of the metric, so basically the scalar, the vector, the split, so the difference between the two scalar, and the tensor. And in that plot, and this is something which is quite interesting, is that in fact in every lines there is three lines. There is the colored one, the dash. The colored one are the result of the simulation. The dash line are second order perturbation theory. And there is a third line that you don't see at all because they completely laid on each other, which are just under the color line, which are the power spectrum that you obtain through a Newtonian simulation using the Green-Wald dictionary to translate the power spectrum. And this is, in the beginning I was thinking this is really a bad result because it means that we don't need to go beyond, we can just use a Newtonian simulation. But at the end I think this is a really good result because at the end the Green-Wald dictionary have used exactly the same approximation schemes as us. So if we were not in accordance with them, it would mean that our code would have a problem, and that's it. So this really is a really strong test to say, okay, performing a cold dark matter simulation is pretty well done with that code. And then evidently, if you change the matter content, for example, if you go to neutrinos, you will see a different picture. So sadly, we don't have yet the full power spectrum of neutrinos because we were fighting with shortness, but now we have kind of find a solution. So maybe I was hoping that we would have the plots for now, but no, that will be in 1 or 2 months. So these are basically the power spectrum of the matter content, so the density contrast computed. So it's basically the difference between the spectrum if the neutrino have a mass and have no mass. There is two ways of computing it. The first one is using the Bosman code class, and the second one is using our NBody simulation code. And we see that at the end we are very well in agreement up to scales of, let's say, 0.1 h over megaparsec. And this part, I don't know. Here is exactly a place where I don't trust my simulation at all. So I don't know what we can say here. So we can have nice pictures, and I like these pictures, and that's why I show you. It's because you can see. Okay,
so in there, just to make a comment, you can't trust class at those nonlinear scales.
Yeah, I think too.
So it's really
I think both code you cannot trust them, exactly.
It's a good thing they don't agree.
So I like this plot just because it shows well what happened with neutrinos. So here you have the halos in your simulation, so it's basically done with a halo finder. I don't remember which one we used. And these are really just the particle position. And this one is the neutrino calculation. And what you see is that even if the neutrinos, and this is exactly what you expect, even if the neutrinos are quite homogeneously distributed, they kind of clumps, but only you will see real change in the contrast only where you have the largest halo. And in the other place you will have
Redshift 0?
What? This is all redshift 0. And yes, and this is the only power spectrum of our metric that we managed to get without much problem due to the shot noise. So it's fine scalar, and you see that if you look at the dashed curve as first order and second order perturbation with the total, and then our NBody code kind of follow quite well at redshift 24, which is what you should expect, because at that redshift linear perturbation theory should be still valid. Then you go up to redshift 1, and you see a small departure. Here, I trust this result. I really trust this departure. The curve that we had was much longer, and we cut it at that level. So here, this small difference exists and is there clearly. But it's also something that you should expect to have this small change. And then one interesting thing that we had with Gevolution is the absence of back reaction. I think it can be interesting for two possibilities. First one would be our code is sufficient and there is no back reaction. Secondly, our approximation scheme doesn't capture back reaction, and it means that we have to go beyond this kind of code. Then, for sure, to be able to answer that question, we have to move out to numerical relativity, because you cannot build up, compute the general back reaction in another way. But you see that what you see here is at redshift 1 something that is order 10 to -6. So if you want to tackle that with numerical relativity, you better to have a code that is able to deal with that kind of precision.
But just precision, it's at what scale?
This is the average of the full box, so it's probably half a gigaparsec. Yeah, give me 1 second. It's half a gigaparsec. It's half a gigaparsec with a resolution of 50 kiloparsec, no, 100 kiloparsec. So, just to advertise that there will be a next release of the first version, the 0.1 version of Gevolution. We have changed some things, and I have not speak about that before, but this is the important things that I want to say about this release, is that we moved from using the evolution equation to get the gravity part to the constraint. That could look a bit weird, but in fact I think it's a really clever trick. Because what is worse? You can think it like that. What is worse? To have a bad evolution of your particle that you know that you have. You know that you are not solving the particle, the geodesic equation exactly. You know that you have problem because you have particle to mesh interpolation and etc. that lead to something like 1% accuracy of the particle to mesh code usually. And I would think that it's much less worse to have that than to have unphysical state. And if you have a constrained relation, is what you have. You have a physical state that evolves in your box, and this is, for my point of view, it's better to have at each snapshot that you take a state which is perfectly physical, but okay, with a not completely correct evolution up to that state. But if this evolution is not completely wrong, it just means that you have, if you evolve back to the past up to your initial conditions, you will have slightly different initial conditions, which are allowed by statistics. And this is, up to the moment you have not completely destroyed the power spectrums, that's perfectly fine, I think that. Then we have a better initial conditions, and I think one really good thing is that now we are able to evolve the neutrino, not anymore really evolving the particle, but we use the class code to get the transfer function, and then we evolve the neutrino using those transfer function, and then we use the neutrino, project them, and get the gravity part. So I think it's a quite of nice trick. Then let's move to numerical relativity. So I think going to numerical relativity, myself, I'm completely new in that scheme. I'm coming exactly in the opposite way of Elisa. Elisa was working quite a long time in numerical relativity. I'm doing numerical relativity for 1.5 years, or 2 years now. And the first, so it's a problem which is clearly not trivial to put in a computer. And I think that you have two elements that are really bad in cosmology for numerical relativity. First one is presence of growing modes. You have growing mode, physical growing modes. So you have to fight to find a way to get rid of them for numerical stability reason. Then the second thing, and this is very well, oh, I should have cited this paper again. This is very well, so where I put this paper? Yeah, it's very well shown in that paper. And that's great because that's exactly what we were thinking. And there was no real test of the constraint relation with n-body up to that paper. So it's 1 month ago. And what you see is that the constraints are completely screwed if you are using the particle. They get error at 10 to, relative error of the constraint relation at 10 to minus 2. So this is kind of clear, big issue. I don't mean that I don't trust their results. It doesn't mean that you have so huge constraint relation that you cannot trust your code for certain behavior. But I'm just saying that currently you have the proof that indeed, if you use particle to mesh, and I was using one of the most elaborated third order particle to mesh methods, it doesn't work with the, it just breaks the constraints. So now we move to the schemes we have developed the last year. So basically it's kind of a very standard starting point, and then it starts to be a bit tricky. So the idea is we start with the usual form of the metric. You write out the Einstein equation. In the standard Adian form, you get those equations. That's basically the same equation that Elisa had shown. Probably I think it's exactly the same one. Then you have to make a few intelligent steps with the perfect free. Which it's really nice because the way we build up this scheme took us like 1 month of math, and 1 month ago we just realized that it can be done in just a couple of lines. So, so basically what you do is you just write out the energy tensor of the fluid. Here are the mass going from this equation to this equation. This is not trivial at all, but it's done in a couple of lines. Then you define, you have the definition of the density. And then if you give an equation of states, let's say constant, we have done just for that, but it probably can be generalized for a more complicated equation of states. You get a definition of the pressure, then it means that you can use those equations to reconstruct the density and the velocity of your fluid, and then it means that you can inject those two variables in that equation, in those two equations, and basically you get rid of the constraint equation. So this should okay, first let's say you get rid of one problem, but you get another one in the other one. So you get rid of the constraint, but then you have the fluid that will evolve, and you have to still to verify that the evolution of the fluid are correct. Evidently, you have basically transferred the problem from the constraint to the fluid. And this is exactly the thing that I was saying to Gevolution. What you prefer, having unphysical state or having a very accurate evolution of your matter content? Myself, I prefer to avoid to have a physical state. Yeah.
How do you know that it's not equivalent? In the sense, you know.
I think myself, I think it is. At the end.
Sorry, what is your question?
It's if it's not equivalent to have the problem on the constraint or on the
yes.
on the fluid.
Suppose that you have an error in the evolution of the fluid, and
this is something that we really have to investigate.
Could be a
But
violation
I
of
think
constraints anyway. In the end, it could, be translated in a violation of the constraint.
But the constraints are pretty strict. Oh, sorry, maybe we discuss.
Yeah, we discuss that later.
Okay.
Yeah. Perfect. We managed. So I think that the very important thing here is that you have the fluid, which are described by this H on this, by H, this curly H, but you can add any other matter content here through this density and velocity field. So basically, you can add particles. You could add any other things that you would like topological defects or things like that. And the constraint will be perfectly respected. Then one trick that you can use, another thing, is that you can set these two H very close to 0. Or to be more intelligent, like 1% of the fluid is there. And the rest of the fluid is there, in particles, for example. It means that you will have the major part of your matter content, which will follow the correct evolution, on a very minor part, which is under lower than your expectation of accuracy of your code, that are completely fake, unphysical fluid. But this is a really good way to get rid of the constraint. And just to look at where. So, one thing, the first times we just tell, oh, we have found a way to put the fluid in the metric, people were like, it's not possible, this kind of thing. And in fact, you have to think about the Bardeen work. Bardeen has done that at linear, at every order, in fact. It has a nice construction that allows that at any order of perturbation theory. Then what it is there, it's just a completion to fully nonlinear. It's exactly the same manipulation, but at full nonlinear order. So what's to just see where you have, okay, so just to think, you have 10 numbers, 2 degree of freedom of gravity, 4 degree of freedom of your fluid, 4 degree of, 4 gauge freedom. So basically you have 10 numbers, 10 things to put in 10 numbers, you should be able to do that. So if you look at where are the fluids, the best way is just to do an harmonical decomposition. What you get is two wave equation. The sound speed here is really the dp over dρ over dp. On this, you see that basically the scalar part now start to carry on the sound speed degree of freedom of your fluid. So you have now a propagating scalar part. And here you have a propagating gravitational wave part, but this was already the case before. And then those two equations can be trivialized because you can choose psi and phi as you want, so you can trivialize those two equations, so there is no degree of freedom here. And then you have those two equations where you have two additional degree of freedom, and these are the rotational velocity of your fluid. So that's it. Then let's go to our schemes. So it's not exactly the equation we are solving. So we do the usually conformal traceless decomposition. This is the same thing done in BSSN, and this is very logical to do it in cosmology. And then we did this decomposition before understanding that was the one of BSSN, because in cosmology it's kind of logic to do that. And then we use that choice of laps. This is a very unnatural choice, and I really don't like it. All my collaborators also don't like it, but it works, so we keep it. So why we really don't like it is because of those integrals. Because here you integral on the space, and basically on a slice at a given time step, we don't have at every place the same redshift. So basically you build up a scale factor from quantity that doesn't belong to the same redshift. So this A is really not a scale factor. Really. Okay, yeah. Then what we do is to choose the shift, we set gamma I to 0, and so it's basically the time, yeah. And this, how to keep this gamma I to 0 is basically we look at the equation gamma I dot, and it gives us an equation, an analytic equation to beta, and we just solve this analytic equation at each time step. That's it. So the schemes look at that, so it's very long list of equations. I don't think it's really worth the time. Then I just want to say that if you linearize this scheme and you go and you look at the stability, you can write back the system like that, and then you get those matrices, and then with those values, and what is really incredible, like the first time I saw that, I was like, no way, that's not possible. You have all eigenvalues are strictly negative. The real part of all the eigenvalues are strictly negative. You have no growing mode. The field you are evolving has no growing mode. I'm not stating that there is no growing mode in the simulation. There is. You have the density contrast that grow. It's clear. But the field that you are evolving doesn't. And this is crucial. And why it's crucial? It's crucial to pass a robustness test on FRW. This is I think the conclusion of this talk is that we are able with this scheme to pass a robustness test on FRW. So what is our robustness test? You take just the FRW background, and then you perturb it with perturbation around 10 to minus 8, 10 to minus, here it's 10 to minus 9. And then it's just to mimic numerical error. And then you just let it evolve. If you have any growing mode in the field that you evolve, this is for sure you will not be able to pass a robustness test. Because in a mode will grow, some quantity will grow, the small fluctuation that you have put in your computer will grow and start to screw everything up. And I think that passing a robustness test is something primordial for going to cosmology in numerical relativity. I mean, a robustness test on FLRW is just because without that, how can we really state if the back reaction that we catch are real effect of back reaction or they are effect of numerical instabilities? Do we have just drawing modes that start in the beginning and they flow, and then around redshift 5 they start to activate and they create an acceleration of expulsion around redshift 3. Youpi, we can get rid of the cosmological constants, yeah, but
Sorry, I have a question, David.
Yeah.
So does that depend on the scale, or the robustness is?
The robustness should be at any scale.
So it is. You've checked.
Yeah. In here, it's at any scale. We checked up to 500 kiloparsec.
500.
Yeah, but we never went below. We don't have the computational resource. Let's finger crossed.
But you said your resolution was 10 kilopascals.
What?
You said that your resolution was 10 kilopascals.
No.
Spatial resolution.
No, I said that at that resolution you really have to start to 10 kiloparsec with Gevolution. Yeah, this is very different problem. So here it's like 500 kiloparsec. But the goal of the simulation has said we are using only a perfect grid. So I think the goal of this simulation is really to look at very large scale and not small scale at all. So you can see that basically you have the three, you have the two scalars and the tensors that kind of decrease with time, and there is only one thing that makes me unhappy with K that grow in the beginning, but basically that's exactly what we were expecting from our theoretical. Basically, when you were doing exactly the same things that the linearization of this thing to see that there is no growing mode, if you do that, but adding some randomness in your system, you get a bit of growing mode in K, and that's exactly what we see here. But these growing modes start to grow a little bit at redshift 100 and then decay from redshift 50. At redshift 50 you are still in the linear. Myself, I would say, okay, you are still a bit linear, so I would trust my code up to that, even if you have growing modes. You are not going in nonlinear scales at that moment still. Then it's a lot of work in progress. For now, we have to set up additional cosmological tests, for example, the linear modes. Usually in numerical cosmology, people are only testing the gravitational waves. Evidently in cosmology, I think they are the least interesting part. No. They are very interesting, we all agree with that, but they are the least relevant for large-scale structure formation. The scalar and the vector are much more relevant. Then nonlinear test, we were thinking of doing an LTV test. There is some difficulty to do those gauge tests that are used in numerical relativity, just due to our formalism. Those tests basically are past yet now. So now we are working really on the cosmological initial conditions, and we are preparing this paper that will be moved to 4 months, let's say 1 year. And then what we are working also in the same moment with testing the code is to add topological defect, global one, not local one, because we don't have yet a formalism that allows to do local defects or gauge field theory. That is gauge field theory on curved spacetime, but this is a work in progress. Then we really have to do ray tracing because, as Elisa was saying, if you want to compare results, and especially if we want to start to compare results between codes that are not using the same formalism, not using the same gauge, we really have to do ray tracing. And finally, it will be adding particles. Let's hope that the next 2 years all this will be gone, and that will be fantastic. I will pass the conclusion, and thank you.
So what is the best mass resolution you can work
with? What? This is kind of a silly question because I would answer with which computer, which how many CPU hours, and then I would say if you give me Tian for 2 years, we can have something like 1 kiloparsec for a 10 gigaparsec box. Yeah, something like that. And that would be, I think, in long term, that would be kind of the goal. going further than that. But then, going at so small scale will really mean that we need to include bionic effects, and then that's a completely new story. Let's hope that I will start this new story.
But in neutrinos, those are much more difficult to barrier.
Yeah.
Well, gadget does the barrier.
Yeah, but it's really, it's not, I think, it's not trivial at all to implement that in a relativistic framework. In a Newtonian one, it's not so difficult because you just have to modify a bit the forces, the smoothing parameter, and things like that, and then you can kind of fix what you want. But I don't know. Currently, I have no clue in numerical relativistic framework how you could include all those things. Not at all. Yeah.
Maybe this is a very basic question on the Gevolution part of your talk. You said the metric perturbations are kept small, but the density perturbation can be high. So is there a discrepancy somewhere?
Yeah, this is very weird. I completely agree with you. That really astonished me. But if you look at the scalar potential, for example, at the surface of the sun, it's 10 to minus 6. So it's small. So it's really very small at any scale, in fact.
You can have large gradients of field.
Yeah, exactly.
Large density. No, it's not unusual.
That's it. Yeah.
Yeah, so I don't know if this ties on to Pierre's question from before, but so have you monitored energy conservation, energy momentum conservation?
Okay,
Because
we have
monitor,
in the LTV test we have monitor it on its works perfectly fine.
Basically, this is the trade-off. To get perfect
I
momentum.
completely agree with you.
Okay.
In the LTV test we have monitored it clearly.
And that is
In
just
the linear
something
test also. Then now in the FRW just robustness test, basically we have not. But I think that the fact that we are able to, because there is not only the fact that we are robust, there is also the fact that we are solving FRW with 10 to minus 9 of precision here on the scalar, on 10 to minus 11, 10 to minus 12 precision. So it's exactly the kind of same numbers that you will get if you are just solving the Feynman equation, and then you with a Runge-Kutta form, this is exactly what you are doing, but there is this small perturbation. And I would say that if the fluid was behaving completely wrongly, we should go away from FRW. That's why we didn't spend the computational time.
Well, you can still be going around the FLRW class. That's you're enforcing the constraint. You don't.
Yeah. But then it means...
Which means that basically you'll be creating matter. Or losing matter. So that's the constraint
that you get. I see what you mean. But if we were creating matter significantly, or annihilating matter significantly, we should get out of the theoretical expectation. Because if you change the matter content, you will not have the exactly same evolution. So I would say... What? We don't? No, the matter is evolved inside.
Okay, so
the degree of freedom are encapsulated inside, so the matter is really evolved. And if you look at the delta, the density contrast maximums, they really follow linear perturbation theory.
Okay, so no, what I was saying is that that's the constraint that you should be, once you lose the Einstein's constraint, you have to monitor the divergence of T mu.
No, I perfectly agree with you, and this is, I think, but as said, for this test, I would say it's not needed, because if we were at a precision of 10 to minus 3 away of FRW, I would say yes, we have to. With this precision, it really means that there is no creation of matter, there is no annihilation of matter. We are following the correct evolution for both the matter content, so it means that it dilutes correctly with the expansion, and for the metric.
Any other question? So let's